Yeah, hello everyone. Thank you for joining again. And did you have time to start doing the homework? In case anyone missed it, I'm gonna send the homework again. But it's the same one, the homework that's related to the last lecture about Bell's theorem. Yeah, if you have any trouble when you're trying to solve these questions, just send me an email, and I'll just put my email again. And probably a few days later, like a few days after the last lecture, we're gonna send you the solutions so you can double check. One other thing that I wanted to say that I should have said last lecture, but I forgot, is I wanted to just give you a reference of a very short paper, just a motivation reference. It's this paper called Why Physics Needs Quantum Foundations. It's by Lucien Hardy and Rob Speckens. They're both physicists here at Perimeter. Rob is my supervisor. And I think it's just 4 pages, and it's just a paper for motivating the area for general physicists. And I think this is cool if you want to see some motivation. So let me also send you the link for that if you're interested. Okay, so this is all in the chat. In that case, I think we can start today. So today I'm going to talk about causal inference. Let me share my slides. Okay, so I suppose you can see this now. And all right, what I'm going to do is I'm going to first talk about classical causal inference, which is because causal inference is a framework for understanding causality that was developed in the 90s by machine learning scientists and like statisticians. And it was not motivated by physics at all. In the beginning, it had nothing to do with physics. And this area has applications in many different places. Like you can apply it to medicine, you can apply it to finance, you can apply it to anything where causality, the concept of causality makes sense. So this is going to be the first half of the lecture, just these foundations that don't have anything to do with physics per se. And then in the second half, I'm going to go back to Bell's theorem and show you how Bell's theorem can be reformulated with this language of causal inference. And then I'll tell you a little bit more about why are physicists interested in this. In the middle, I'm going to give you a 10-minute break. And again, like last time, if you have any questions, just don't feel shy, just interrupt me, okay? I really prefer that you interrupt me than you being lost. And as I figured out in the middle of last lecture, I can also see the chat while I'm sharing slides. So if you prefer to send in the chat, feel free. But if you want, just interrupt me. That's fine. Okay, so as I said, first half is classical causal inference. Every time I say classical, I mean not quantum, like things that any statistician would be interested in. So let's start with very simple examples, very silly examples. So suppose that you're in a certain city in the coast, and you see that there is a correlation between the number of ice cream sales and the number of sunburn hospitalizations. So every time the ice cream sales go up, more people go to the hospital because they're sunburned. Does it mean that ice cream causes sunburn? Obviously it doesn't, because correlation does not imply causation. And in this case, it's very easy to see what's going on. What's going on is just there is a common cause, which is like the heat or the sunniness. So if it's super hot, more people are going to buy ice cream, more people are going to get sunburned. Sorry, I didn't share the slides in the chat. Okay, let me share. Okay, there you go. Oh, sorry, I sent to only one person. Let me send it to everybody. Okay, good. Okay, so in this case, it's super easy to understand what's going on. Just you have one common cause that causes the correlation between those two variables, the sunburn and the ice cream. Okay, this is the basic idea of what we're going to do in causal inference. Is basically, if correlation does not imply causation, then what is causation? Then how do we find out what is the underlying cause for things that are happening? Now we're going to go to other examples, and I'm going to ask you if you can figure out some puzzles. And if you can't, it's okay. But let's see. So imagine that you are... sorry, one last thing. This thing is called a DAG, which is a directed acyclic graph. So maybe I'll be saying DAG, DAG, DAG many times in the lecture, and maybe Ela is going to say it in the next lecture as well. And what it means is just a causal structure. A causal structure is a graph, so like a lot of points with edges between them. But these edges have to be directed to say that this thing, which causes this thing. When this happens, we say that the thing that's in the beginning of the arrow is a parent, and the thing that's in the end of the arrow is a child. So here, heat is a parent of both sunburn and ice cream. And it has to be acyclic. Otherwise, like we'd get something like a grandfather paradox, and we're trying to avoid that. So yeah, this framework is going to be based on that. But now let's think about something else. It's a paradox in statistics that people call Simpson's paradox. So in this paradox, imagine the following scenario where you have a new drug for a certain disease that you want to test to see if this drug is good or not, like a new treatment. And you divide your sample of your subjects in two groups. The group of people that are younger than 50 years old and the group of people that are older than 50 years old. For both groups, you give the treatment to some of them and no treatment to others. And then you're going to go and check who recovered out of the people that got treatment that are younger than 50 years old, who recovered out of the people that got no treatment that are younger than 50 years old, and same thing for the people that are older than 50 years old. Suppose that you got this data. So what this means is that among the people that are younger than 50, you gave the treatment to 300 of them, and 180 recovered. So this is the number of recovered people. So 60% recovered. But among the people that got no treatment in this group of younger than 50, 100 people got no treatment, 70 recovered, so 70%. So this means that in this group, the treatment was bad because the people that got no treatment recovered more often. Now, among the group that is older than 50, you did the same thing. You found 20, 30. So that means that for both groups, the probability of recovery when you're treated is smaller than the probability of recovery when you're not treated, both for younger than 50 and for older than 50. So it looks like the drug, like the treatment is bad, is harming people. Now, let's look at the total. Let's clump together the groups of younger than 50 years old and older than 50 years old. Okay, so this last line here is just the total number of people that were treated. So it's 300 plus 100 for 100. And here the total number of people that recovered. So 50% in the end of the total number of people that were treated, recovered. And among the people that were not treated, you have 40%. So now it looks like the probability of recovering, given that you're treated, is larger than the probability of recovery, given that you're not treated. And this is in contradiction with those two other inequalities above, because it looks like the treatment is bad for people younger than 50, bad for people older than 50, but good for the total of the population. Does anyone have any idea what is going on here? I'm going to give you a few minutes to think, and then I'll say the answer. And you can also just ask clarification questions if this is not clear.
Hello?
Yeah?
Please, can you hear me?
Yeah.
Will it be okay if we could go over the question again, please?
If I go over the question again, sure. So the thing here is that you have this population of people, like they are your subjects. You are a biology researcher. You're going to see if the treatment is good or not. You divided the population in two, of people that are younger than 50 and people that are older than 50. Okay. However, among the people that are younger than 50, it looks like the treatment is bad because the people that were treated, 60% recovered. But the people that are not treated, 70% recovered. So not treatment was better. Among the people that are older than 50, same thing, not treatment was better. However, if you just sum everyone, so this last line here that is the total, is the total number of people that were treated, so 400, 300 plus 100, and the total number of people that were treated and recovered. So 100 plus 180 plus 20, 200. So here it was 50%. If you do the same for the total of people that didn't get a treatment, then it's 40%. Now it's smaller than here. So if you look at these inequalities here, it looks like the treatment is bad for this population that is younger than 50. The treatment is also bad for the population that is older than 50. But if you look at the total, that is like just anyone, then it looks like the treatment is good. So would you tell your patient to take the treatment or not? That's the question.
Thank you.
I think in this case, there might be a need for another variable or like some other, because then otherwise it's confusing. So you need some other factor to consider. So maybe there are factors that we are not considering. Maybe people older than 50 are the reason why the numbers change or something. So if we could find out that, okay, those older than 50 is because their cells are something, and that also leads to whether they respond to treatment or not, then maybe we can.
Yeah, that's in the right direction. That's a good hunch. Like maybe there is some variable here that influences, because basically we're trying to see if the treatment causes recovery or not. But the variables that are important here are not only treatment and recovery. There is another variable that is also important. Can anyone have a guess here?
Yeah, hello, can you hear me?
Sorry?
Can you hear me, please?
Yes.
All right, so I'm thinking it's because the number of people who got treatment and those who didn't get treatment is unequal. So it's, I don't know, it affects probability in some way. I think
Yes.
that's my guess, yeah.
Yes.
The number
Good.
of people, yeah.
Yes, that's it. Now let's see more detail. This is the kind of idea. Both ideas that were given, they complement, and that's the answer. So let's go slowly through it. This is the table again. However, as they said, notice that the people that were younger than 50, they are more likely to get the treatment. So 300 out of the people that are younger than 50, the majority got treated. So 300 versus 100. But among the people that are older than 50, the minority got treatment. So only 100 here and here 300. So it's, we think, like before, we thought that the DAG should be like this, like the treatment, either like there's an arrow, it could be positive or negative. So the treatment influences the recovery either in a good way or in a bad way. So the treatment influences the recovery, but also the age influences the recovery. Note that the people that are older than 50, they're less likely to recover anyway, just because their health is worse because they're older. But if it was just this DAG, that would not explain why you have this difference in the total. The problem is, so age is the extra variable that the first person mentioned. However, the problem here enters because of what the second person mentioned, that is, the number of people that got treated depends on your age. So the fact that you're going to get treatment or not also depends on your age. Because if you're younger, in my experiment, since my experiment was badly designed, you're more likely to be treated if you're younger. So then age also influences treatment. So this is the correct causal structure, not the previous one. Age influences both recovery and treatment. So what does it mean? This means that even if so let's first see a graph. So you can see that this is the kind of distribution of the data. Among the people that are older than 50, so here in blue, less people get treated. However, the treatment is bad for recovery. You see the line going this direction. Among the people that are younger than 50, also more people get treated, but the treatment is also bad. So the line goes like this because the treatment is bad. However, if you clump everybody, it looks like the treatment is good. And the underlying reason is because of this graph. So this age, that is the common cause, it's going to create a positive correlation between treatment and recovery. So in other words, oh yes. Do you want to talk? Sorry, I cannot hear you. Okay. So in that case, so what I was saying is that this common cause, that is the age, is going to create a positive correlation between treatment and recovery. However, this is why you see that when you clump together by age, it looks like treatment and recovery have a positive correlation. However, when you stratify, treatment and recovery have a negative correlation. And that's because the fact that you're younger makes your recovery so much better that even if the treatment is being bad for you, when you're compared to people that are older, even the people that they're treated with the bad treatment, they're younger, this is kind of going to compensate. So if you look at this DAG, this arrow, this causal arrow here between treatment and recovery is going to be a negative. It's going to be kind of negative. So the treatment is bad for recovery. But the age is going to create a positive correlation because people who are younger are more likely to take the treatment and they're more likely to recover anyway. People who are older, less likely to take the treatment and less likely to recover anyway, even regardless of the treatment. So the conclusion here is that the treatment is bad for everyone. And also the conclusion is that if you only look at the statistical data, like if you only look at the table without thinking about the causal structure or like the underlying causal explanation, you might get confused by those things. Does this make sense? Are there any questions on the Simpson's paradox?
I think it's okay.
Yes?
Okay. Oh, can you hear me?
Yes.
Well, why the difference in the sample space for treatment for younger than 50 and also older than 50? Because for younger than 50, we have 300, and for older than 50, we have just 100. Why don't you have the same sample space?
And no, I mean, this is just a scenario. So imagine that someone gave you this data. It's just that. So of course, this is not the best possible experiment. The best thing you could do is to make the same. But the paradox comes from the situation where someone gave you this data, they made the experiment like this, you don't know why, and you have to interpret the data.
Oh, okay.
Yeah, it's kind of a badly designed experiment, but like, how do you get information from this, even if it's a badly designed experiment? This causal analysis show you that you need to look at the stratified information. Any other question?
What does the Simpson's paradox tell us in the end about causation and correlation?
Yeah, so I think that the important thing here is just noticing that if you only look at the correlation, you might get confused. Like if you only look at the table statistics, it's hard to see why would the stratified one be a better data than the total one, right? But if you look at the causal structure, then it's very clear that the age is influencing the treatment here. And this common cause here is creating this positive correlation. And actually, what's important is the stratified data, because you want to know about this arrow. When you do the stratified data, is basically you don't have the stratified, I mean, either only looking at younger, only looking at older. Then you don't have this confounding by the common cause anymore. So people sometimes, when there's a common cause, they also call it confounding. I don't know why. I think it's because it's confusing, because it makes you confuse causation with correlation. So here you're going to have a correlation that doesn't come from direct causation. It comes from the common cause, age. So actually, you need to look at one specific age to then see whether what is the correct causal relationship between treatment and recovery. So I think this is what we learn, is like the importance of looking at the causal analysis and not only the statistical data. If you go back to the example that we had before with heat and sunburn hospitalizations and ice cream sales, it's kind of the same thing. So you might think that there's a correlation between ice cream sales and sunburn hospitalizations, but that's only because of the common cause, the heat. If you knew exactly what's the temperature, so if you stratify your data by temperature, then there's no correlation anymore between sunburn hospitalizations and ice cream sales, because those are completely uncorrelated. This case, it's a more extreme case. It's a case where treatment and recovery, they're not uncorrelated, they're negatively correlated. But the common cause is so strong that makes them positively correlated. Does it make sense?
Yes, it does.
Okay. Okay, if there are no more questions, I'm going to the next example, but you can always ask me to go back if you want. So the next example, okay, so first I go back to the sunburn hospitalizations, and I'm going to say exactly what I just said. So when you know exactly what is the temperature, So what is like the heat? So you know exactly what is the common cause. Then this explains all of the correlation between sunburn hospitalizations and ice cream sales. So now they're going to become uncorrelated. This notation here means conditional probability. It basically means what is the probability of SI taking a value given, so the bar is like given that you know what is the temperature H. So given that you know what is H, this causal structure tells me that S and I have to become uncorrelated. So then the distribution has to factorize. And that's because there's no arrow between them. And no other common causes. This is the only common cause. Okay, so this means that this causal structure, where you have H pointing to S and I, can only explain your data if your data satisfies this equation, okay? If your data doesn't satisfy this equation, then you know that there must be either a direct arrow between those two or another common cause. So, for example, in this case, if you know exactly what is the age, treatment and recovery, they don't become uncorrelated. They still correlated, but now they're negatively correlated. Okay, so this equation is then a restriction on which probability distributions are compatible with this causal structure. Like every probability distribution that can be explained by this causal structure has to obey this equation. So that's the general philosophy. We have a probability distribution that is the thing that we observed in the laboratory. And we want to know what are the underlying causal explanations that could explain your probability distribution. So you're going to look at what are the restrictions, what are these constraints that each causal structure imposes, and your probability distribution has better obey the constraints of the causal structure. Otherwise, it cannot be explained by that causal structure. There are other variables that you could also that could also be important to explain the data that you're observing, but that don't appear directly in the probability distributions. One example is like the sun protection awareness, let's say. It influences only sunburn hospitalizations. It doesn't influence the other two. However, it is very hard to measure. So you're not going to measure it. This is, I'm going to call this a latent variable. It's a variable that we know it exists, like we think it exists in our causal structure. We think it helps for causal explanations, but we don't have data about it. So every time we see which probability distributions are compatible with the causal structure, we're going to see only the probability distributions over S, I, and H. A is going to be marginalized, but the variable A is going to help in the causal explanation. And these are going to be latent variables. Here, I'm going to represent them in red rectangles for now. So a probability distribution has to obey this equation to be compatible with this causal structure. Basically, this is what a causal structure says. This is the meaning of a causal structure. It's that a probability distribution over the visible variables, visible meaning the not latent ones, the ones that you actually go and get data in the lab, they have to factorize in this way, such that every variable only depends on its parents. So S, what are the parents of S? Are A and H. So here and here. So it factorizes as P condition on the knowledge of A and H. I condition on the knowledge of H. That's the parent. H doesn't have any parents, so just P of H. And A also doesn't have any parents. And you have to sum over the value of the latent variables. So basically, latent variables are variables that you didn't measure for some reason. Either it's impossible, it's unethical, it's for some reason you didn't measure it, so you don't know what is the value of that variable. In statistics, when you don't know what is the value of that variable, you marginalize it. So like you sum over all possible values. So does it make sense? This is kind of the definition of what it means for a probability distribution to be explainable by a causal structure. It has to factorize as children given parents, and in the end, sum over all the latent variables. Any question here? Okay, so note that when I told you that the distributions that are compatible with this graph have to obey that factorization. So this factorization, Si given h equals S given h, I given h. This is a consequence of this equation. This equation is like the definition of being compatible with this causal structure. So that one, that's like when you know exactly what is h and S and I become independent, it's a consequence of this equation, because here, like you also factorize, like after you marginalize over A, you also factorize S and I when you condition on H. Okay, this definition is going to be important only towards the end of the lecture. Now we're going to continue just thinking about the more intuitive notions of what it means, like for a causal structure to explain a probability distribution. So now I'm going to go to another example. I think this is a fun one, and I'm also going to ask you questions in the middle. So suppose you are a researcher in the 1950s, and you want to find out if smoking causes cancer or not. The data is very clear that shows a very strong correlation between smoking and cancer. So the more, I put the X is wrong, but basically the more people smoke, the more likely they are to get cancer. And this is very obvious from the data. There's a very strong correlation. However, the cigarette companies, they come and they say, no, but correlation does not imply causation. If smoking and cancer are correlated, this is not because smoking causes cancer. This is because there is a gene that people who have this gene, they're more likely to want to smoke, and they're more likely to develop cancer. And note that this gene is impossible to measure, like with the technology that we have right now. We are in the 50s. And also, we don't know which gene it is. So here it is red. It is a latent variable. So you cannot just measure it to see if there's any causation between smoking and cancer remaining or not. And then you're skeptical about it. You're like, okay, even if that is by the way, this actually happened. There was people that proposed this type of causal explanation back in the day when people were trying to find out if smoking causes cancer or not. And I want to, okay, now suppose that you, the researcher, you're a bit skeptical about it. You say, okay, even if there is this gene that is very weird, even if there's this gene, I think there's also a direct causation between smoking and cancer. I really think that's the case. How can you test which one is the correct hypothesis? Do you have any idea what is a possible way that you can go to the lab, make an experiment, and figure out? I'll also give you some minutes to think. Someone asks, is there a possibility that there are people who have cancer because of the gene but don't smoke? Definitely, but the problem is that here, those causal structures, they don't mean a deterministic dependence. So it's not 100% of the people who smoke that have cancer. It's not 100% of the people that have the gene that have cancer. It is just a probabilistic dependence. So like people who smoke or people who have the gene are more likely to develop cancer. So even if you see that there are people who have cancer but don't smoke, this doesn't prove that smoking doesn't cause cancer, because it's just some higher probabilities, not 100%. And that's what we see in reality, right? Right now we know that smoking causes cancer, but it's not everybody that smokes that's going to develop cancer. But just between those two causal explanations, how would you find a way of figuring out which one is the correct one? Okay, someone said we can round up people who smoke and have cancer. We find out what is common among them. Then we see if there's a particular trait which cuts across. Okay, that's a good idea. But how would you, like, suppose that you find a common trait among them? How, like, I want more specifics. Do you have any idea of more specifics of seeing a common trait that says, okay, definitely there is causation between smoking and cancer, or definitely there is no causation?
Well, I think in this case, I can use the data to see if the distribution that you've provided previously, if any of these diagrams satisfy that distribution, then the one that satisfies that distribution, then it will be the one that is the correct simulation of the situation.
The problem here is that if you have one latent common cause, so maybe I should have made this clear. If you have one latent common cause that is like the gene, that is a common cause that you cannot observe, pointing to two things, this can explain every correlation between two things. So every distribution between smoking and cancer can be explained by a latent common cause, if this latent common cause is powerful enough, like if it creates a strong enough correlation between them, it can explain anything. So every probability distribution over those two variables, S and C, like smoking and cancer, can be explained by this and also can be explained by this. So the thing I showed before, it has some redundancy, like there's more than one causal structure that can explain the same probability distributions. And that's the difficulty here. So someone here said, maybe computing the probability from both causal structures, choose the one with the highest probability as most relevant. Yeah, so I think, again, there's the same problem that I said. The causal structure doesn't give you one probability distribution. It gives you one set of probability distributions that could be explained, because we allow the latent variable to be anything. So if this latent variable is powerful enough, both of them can explain every probability distribution. Someone says, since genes are inherited, we can do a background check, like looking into the families. We could then check if there may be grandmas or granddads or like family who smoke, or those who have cancer, or those with both, and check from there. Okay, that's a good idea. I actually haven't thought of that one before. But I think, what if then there was another hidden factor? I think the general feeling here, like I said gene just to make it more concrete, but the general feeling is, how do you explain that the correlation doesn't come from a hidden factor? Like that could maybe not be the gene. And like, I don't know, another hidden factor, like age. If you're older, you're more likely to smoke and more likely to have cancer. Or, I don't know, your diet. If you eat badly, this is correlated with smoking, and this is correlated with having cancer. And other types of hidden factors, that there are so many hidden factors, that there's no way you can account for every one of them, like you're trying to do for gene. So the way out here is not trying to account for a hidden factor. Yes.
So I'm thinking that, so like how you explained the first causal structure, you explained that there was a limit, and then when one broke the limit, it meant that this causal structure actually was the one that explained the whole phenomenon of the sunburn and then all that. So if we want to check if there's going to be some latent variable, then we should establish some kind of limits. That's okay. If smoking actually causes cancer, about 70% of people smoke, therefore 65% of people should have cancer. So then if we realize, and from statistics, and see that if 70% of people smoke, it's only about 10% that has cancer, then it does not probably meet the limit, or does not surpass the limit, and then it probably means smoking does not cause cancer.
So I think that the problem here is that in the example I gave of the Simpson's paradox, I knew how to stratify the data. It was by age, right? Like, it was like, these people are younger, then they blah, blah, blah. These people are older, then they blah, blah. So then when I stratify by age, I could see, okay, the treatment is bad. But when I only had the total, like the one that's not stratified by age, then I couldn't know if the treatment is bad or good, because the total showed me that the treatment is good, but it was wrong. Here, in this case, it's as if I only have the total. So when I say total, remember that we sum over here, we sum over latent variables. So this is what I mean by total. If you have a variable that is hidden, it's like you're summing over them, or like you're taking the total of older than 50, younger than 50. And here's the same. You're taking the average of the population. You don't stratify by gene. So it's like you're summing over gene. You're taking the total. There's no way to get that stratification. And this limit that you're saying, it was only because I had the stratification and I had the, yeah. So here the problem is that it doesn't matter how strong is the correlation. Even if the correlation was perfect, was like 100% of the people that smoke get cancer. And if you smoke, you for sure get cancer. If you don't smoke, you for sure don't get cancer. So like the strongest possible correlation one can think of, it could be explained by both causal structures, because it could be just that they're copying that smoking comes 100% from the gene and cancer comes 100% from the gene. So in theory, both causal structures could explain everything. I'll give a few more minutes for a last guess, and then I'll say at the end. Maybe think about how one thought that's there are two ways to do this, and the first way, think about how people actually do drug tests in the laboratory. How do they actually do it to get rid of possible common causes? Are there no more guesses? Okay, if there are no more guesses, then I'll say it. The first way is the way people actually do it in the lab, not for this case, but like for drug tests, is they do the blind trials. They give, for half of the people, they give the drug, for half they give a placebo, and the person doesn't know. So this means that the person doesn't have the choice of whether they're going to take the drug or not. And this is good because, like, for the experiment, because if the person had the choice, then you had drug treatment, and then you could have a common cause. That is, like, if the person is more health aware, if they care more about their health, then they could choose to take the drug, and they could also recover for other reasons, like because they eat well. So in a drug trial, the researchers don't want these other common causes. They want to just see if the drug causes the recovery or not. So then they take away the option of the person taking the drug or not. They either give them the drug or the placebo, the person doesn't know. This type of thing is called an intervention. So it's not just an observational experiment where you just look, it's an intervention. How would an intervention look like in this scenario? You force someone to smoke, you see if they develop cancer or not. Of course, it's not ethical at all. So in this scenario, this is impossible. So there's another way that I'm going to talk about now. But do you understand the idea of the intervention? That, like, if you force a group of people to smoke, and it's a big group, and you force another group to not smoke, then the causation, the relationship like with the gene is cut, because before the gene caused the smoking or not, but now since you, the experimenter, are choosing if the person smokes or not, then the gene doesn't influence anymore. And if you still see a correlation with cancer, then that means that there is an error here. Does this one make sense? Okay. If there are no questions, then I'll go to the second one. That is...
Sorry.
Yes.
Sorry, I do
ahead.
have a question. Yes.
Yes.
Well, in the case of a drug test, well, it is possible for the investigator to control whether to give the drug or not. But in this case, how do you control whether to
Exactly.
To force someone to smoke.
Exactly. It's very bad. You're right. That's a very bad answer. This is why I'll have the second one. That is the best one. So that's the thing. Like for many years, like people thought that the only way of finding out about causal relationships is by making interventions, which is like the drug, like the forcing people. In this case, it would be impossible to say anything about causality in the case of smoking and cancer. Because as you said, you cannot force anyone to smoke. Like it's unethical and also very hard. More recently, like since the 90s, since this area of causal inference was developed, there were techniques that were developed to find out about causal relationships without making interventions. And it's a very interesting technique that I'm going to tell you now. So you look for another variable. Somebody said that like you look to see if there is something in common with these people that smoke and have cancer. So you look for another variable that you are confident it only influences smoking and nothing else. So for example, your peer group. So if your friends smoke, you're more likely to smoke as well. But we're going to assume that the specific gene for smoking and cancer doesn't influence your peer group. And we're going to assume that your peer group doesn't influence cancer directly, because that would make sense. So you need those assumptions. But if you find this variable, and it's a variable that you can measure, so peer group now it's also blue, is also a visible variable. Now with these three variables, you can see if there is a causation between smoking and cancer or not. Looking at those two graphs, can anyone tell me why now it's possible to differentiate?
Yeah, I think it is possible to differentiate now because we have introduced a measurable variable and you have ruled out the other variable which is not measurable.
So, but what is the difference? Like, what is the thing that you would see in the data that would tell you there is definitely causation between smoking and cancer? For example, if you see that there is a correlation between the peer group and cancer, like if your friends smoke, you're more likely to have cancer. Can this be explained by the first causal structure? No, right? Because here there is no path between peer group and cancer. So in this first causal structure, if smoking really doesn't cause cancer and the correlation comes just because of a gene, there's no way to explain why having friends that smoke makes you more likely to have cancer. Right? Because there's no common cause between peer group and cancer. And there is no like path, no causal path between peer group and cancer. Now here, you can explain the correlation between peer group and cancer. And that's because if your peer group smokes, you're more likely to smoke. If you're more likely to smoke, then you're more likely to have cancer. And there is a direct causal path here. But here, there's no causal path and no common cause. All right, so in this causal structure, you need to obey this constraint, that the probability of peer group is independent of the probability of cancer. But this causal structure, on the other hand, can explain a correlation between those two variables. Are there any questions here? Is this idea clear? So this is called instrumental variable idea, because the peer group is like a variable that is not the variable that you're interested in. It works as an instrument to find out if there is a causal relationship between the variables of interest or not. So this instrumental variable technique, it's very cool, I think, because like you have two causal structures that if you look at just them, like without the extra, without the extra variable, then they look, they are indistinguishable. Like, how can you distinguish them without forcing people to smoke? But if you add this extra variable, then now you can distinguish them by just seeing if there is a correlation between your friend smoking and you developing cancer. And I think this is very cool. Actually, this idea of the instrumental variable, I think it won the Nobel Prize of Economics in 2023. And I think this is another trick that we can do in causal inference. that like to figure out what are the causal relationships between things without having to make interventions, like only by looking at observational data. You just look at more data, and then you can definitely find you can definitely prove that there is causal relationship between smoking and cancer. Okay, given this, yeah, feel free to just stop me to ask questions if you are confused, but I'm going to move on to the next topic. That is, I'm going to introduce you the idea of fine-tuning. So to introduce this idea of fine-tuning in a causal structure, first, I'm going to think about a cryptography example, just to explain the idea. So in cryptography, we have a message that is just going to be a string of bits, like 1 and 0. And we have, we want to encrypt this message. So I have a key that is another bit string, and the encrypted message is just summing the key with the message with some modulus 2, where 1 plus 1 is 0, 0 plus 1 is 1, and 0 plus 0 is 0. Okay, so this is a third example now, not related to the previous ones, where I'm going to explain this other concept. Okay, so now let's imagine a super simple example where the message is just 1 bit, the key is just 1 bit, the encrypted message is just 1 bit. And let's imagine that for some reason, I know this is not realistic, but I just want to use an example to explain what I'm interested in. For some reason, you know the message, you know the encrypted message, but the key is a latent variable. So it's red is like the gene, it's hidden. So you know ME, but you don't know K. And now let's suppose that the functional dependence between these things. So remember when I said that everything in a causal structure only depends on its parents. That means that there is these functional dependencies between children and parents. So the functional dependence here is going to be the one that I explained before. So it's a sum modulus 2. The encrypted message is m plus k modulus 2. So it depends on both of its parents. And the key, here actually, there shouldn't be an error between key and message, okay? It's just an error between key and encrypted message. So the key, we do not know what is the key, okay? So I'm going to write it in this way, as just a way to write a probability distribution. That means that it has half chance of being 0 and half chance of being 1. This is just uniform distribution that we assign when we don't know what the variable is. And now I'm going to ask you, what is the encrypted message when the message is 0? So if M is 0, what is the probability distribution over E, given that E is just M plus K modulus 2? Can anyone tell me?
Please repeat the question.
So I have 3 variables, E, M, and K. And I know that E is M plus K modulus 2. However, K is unknown. K is like, I know that it's distributed, like that it has half chance of being 0 and half chance of being 1. Now I'm saying, when M is 0, what is the probability distribution over E, only E? Meaning, what is the chance of E being 0? What is the chance of E being 1?
Well, if 0 plus 0 is 0, 0 plus 1 is 1.
Exactly.
Well, I'm guessing it's 50-50. Yeah.
Exactly, 50-50. So half, just like here. And when M is 1, then same thing.
Also
so
50.
0, yeah, 0 plus 1 is 1, 1 plus 1 is 0. So also 50-50. So this means that that's interesting. M is a cause of E, but if you don't know what is the key, it doesn't matter what is M, you're not going to know what is E. So M cannot signal to E. This means that in this probability distribution, you have this factorization. M and E, they are independent, meaning that like the distribution over E is the same, regardless of what M is. So M and E are independent. But note that M and E here, they have a causal relationship. So this equation here is not a constraint of this causal structure. Remember that before I had shown you like constraints, like the peer group and the cancer have to be independent in order for that causal structure to explain your data. But here, the M and E, they don't have to be independent for this causal structure to explain the data. But in this specific data that I chose, they are independent. So this is called fine-tuning. And this here, so I'm saying that M cannot signal to E because it doesn't matter what is M, like I can change M to be 0, 1. E is not going to notice the change because the E is still going to be like unknown. So the conclusion here that is going to be important for the second part of the lecture is that signaling needs causation, but you can have causation without signaling. So basically for M to be able to send messages to E, then you need to have like some causal path between M and E. But here's an example where I have a causal path, but M is not able to send messages to E. Okay. Oh, sorry. And I was just going to say that this is called fine-tuning because you have to tune exactly what are the parameters in your causal model. So this only happened because the functional dependence was exactly M plus K modulus 2. And the distribution over key was exactly half-half. If the distribution over key was different or this functional dependence was different, then you would not see this independence, like then M would be able to signal to E. So then this thing, when you have causation but not signaling, it's called fine-tuning because it only happens when for very specific choices of the functional dependencies. Okay? Does it make sense? So basically fine-tuning is when you have your set of data and you have your causal explanation and there is an independence or a conditional independence that is like independence when you condition on something. There is a conditional independence relation like of this type that appears in the data but not in the causal structure. It's not required by the causal structure. Are there any questions here about fine-tuning? This is the last thing before we have, basically the last thing before. So if you have any questions, don't feel shy to stop me if you're confused, okay? All right, so this idea of fine-tuning here, it's going to be useful later in the lecture. And this tricks that I explained to you to like try to find out what is the actual causal relationship between things, what is the or because this is the actual question that you want to answer many times. Like you want to know if the treatment causes the recovery or not. You don't want to know if the treatment is correlated with the recovery. So this whole area of causal inference has a ton of applications to classical data analysis. So here are some examples. This paper here in particular, I wanted to talk about it, that there is this guy, Kieran Lee. He was a master student of my PhD supervisor. And after he made a master's and a PhD, he went on to work in industry. And then he had a job at this health company that had an AI algorithm to make diagnosis. Like you input your symptoms and then the app gives you a possible diagnosis. And the algorithm was performing very bad before he entered there because basically they were confusing correlation with causation. So one example that is very cool that he gave us was that the algorithm was saying that when the person inputs that they're having chest pain, the algorithm was saying that it could be diabetes. However, diabetes does not cause chest pain. And why was the algorithm saying that? Because obesity has a very strong correlation with diabetes, and obesity also has a very strong correlation with many other things that cause chest pain. So then obesity was kind of acting as a common cause, or like a common, and you can notice that like the correlation between diabetes and chest pain comes through obesity. It's not because there is a causal relationship. And then the app was performing very bad. So then Kieran went there to this company, and then he helped them implement an actual causal discovery algorithm, and not just an algorithm that looks at correlations. And this improved the efficacy of the app in like a huge amount. So yeah, in case, does anyone have any questions in general about anything I spoke so far on classical causal inference? So are there any final questions? Now I'm going to talk about the relationship with Bell's theorem. So let's go back to a little bit of what we saw in the last lecture. So if you remember, in the last lecture, we had this game where you had Alice and Bob, and then the measurement settings were X and Y, and the measurement outcomes were A and B. And in the case where you have classical strategies, the strategy, we were calling it lambda, which is sometimes called the hidden variable as well. So then, if we want to represent what is going on, what is the underlying causal structure of reality here, we're going to have 5 nodes. 4 visible nodes. Now I'm going to change the notation. So if you remember the visible nodes, they were blue boxes, and the latent nodes were red boxes. Now I'm going to use triangle for visible, and like these red circles for latent, okay? So lambda is like in an experiment, it is the hidden variable. So it's something that we don't necessarily have access to, because in the end, me, the referee, so Alice and Bob, they can discuss their strategy lambda, but what I care about, the referee, is just their outcomes, like the cards that they gave me, and the inputs, like the questions, if I ask 1 or 2 to each one of them. So the probability distributions of interest here are just the probability of AB given XY. So the outcomes given the settings. What is the most natural causal structure that you could have involving those 5 nodes? That kind of follows what we see in the Bell game. It is this causal structure that we call the Bell-DAG. Note that here you don't have arrows, for example, from X to B. And this is because we're assuming that there's no causation outside of the light cone. Remember that they were space-like separated. We assume there's no causation outside of the light cone. There's also X and Y. They don't have any causes here. They're freely chosen. No arrow between A and B as well. And the common cause, it influences what are the outcomes, because the strategy influences what are the cards that Alice and Bob are going to show. So this is the Bell-DAG. Now, let's forget everything that we saw in Bell's theorem and think in the Bell theorem lecture, and think only about this causal inference lecture. So let's look at it as a DAG. And for a second, let's not think about Bell experiment. As we saw, the causal structures, they are such that the nodes, they like the definition of a distribution being compatible with this causal structure is basically that the distribution has to factorize in a way like this, where each node depends on its parents. So P of A given X lambda, which are the parents of A. P of B given Y lambda, which are the parents of B. And then P of lambda doesn't have any parents. Here, I did not put P of XY because on this side, XY is conditioned upon. And then you have to sum over the latent variables. So here you sum over lambda. So this is the condition like for a probability distribution to be compatible with this DAG. That comes from causal inference. That still doesn't have anything to do with physics. You can just look at it as a DAG, just like any other DAG that we were looking at before when we were talking about cigarette or treatment. Okay, so what are the consequences of this equation? You can make the calculations that I'm not going to make, and figure out that if a probability distribution can be factorized in this way, then it has to obey two types of constraints. First, it has to obey those equality constraints, and it has to obey Bell inequalities as well. So the first one, they are no signaling constraints. What do they mean? So if you look at this first one, P of A given xy equals P of A given x. It basically says that y cannot send messages to A. Remember when we saw about signaling when I was talking about fine-tuning? And I said it's kind of about sending messages. So here you have this independence, A being independent of Y. So Y cannot send messages to A. And this other independence is the symmetric one, X cannot send messages to B. And it's very good that this causal structure has these constraints, because if these constraints, like, we never in the real life, in the laboratory, observed an experiment where two things are space-like separated and these constraints are violated. So these constraints, they're always valid in the laboratory because they basically say that you cannot send signals faster than the speed of light. In the case where in Alice and Bob are space-like separated, of course. Yeah, so this is just saying that you cannot send signals faster than the speed of light. When we say no signaling, it always means no superluminous signaling. Okay, and the other constraint that P of AB given xy has to satisfy is the Bell inequality, which is that one that we saw last lecture. That was like the probability of winning the game is less or equal than 75%. 75 was the number for classical, for classical strategies. And here we have a classical causal structure. But as we also know, quantum mechanics, as you've done in your homework, and also experiments, they violate this inequality. So what does this mean? This means that this causal structure that we wrote down does not explain the quantum predictions. So we go in the laboratory, we make the experiment, we see a probability distribution P of AB given xy that cannot be explained by this causal structure. So then we need to find other ways to explain this probability distribution. Is there any question up to here? Like up to this causal modeling of the Bell scenario? Okay, if not, remember the Bell's theorem that I said in the last lecture? It was these four things. It was like those four assumptions: classical strategy plus relativistic causal error plus independent settings plus some background assumptions that I didn't talk much about, give you Bell inequalities. Now, I will show you that the Bell DAG encodes all of those assumptions. So this DAG is kind of a short way to say all of those things. The first thing is classical strategy. So classical strategy comes from the fact that there's nothing quantum in this DAG. This DAG is just exactly the same type of DAG as the one that we were talking when we spoke about disease and cigarettes. So here lambda is a classical random variable, nothing quantum. The second assumption is relativistic causal error. Relativistic causal error basically says that the causes of events have to be in the past light cone of that event. If you haven't studied relativity, don't stress about what this means. In our case, this just means that there's no arrow between X and B, there's no arrow between Y and A, and there's also no arrow between A and B in any direction. So those two things are space-like separated, so there's no causal arrows between them. This is the assumption. And that's the relativistic causal error assumption. The other assumption is independent settings. That basically says that the free choices do not have relevant causes. If you remember from last lecture, this was saying that me, the referee, I am not going to be bribed. I'll choose to have X and Y being random, such that Alice and Bob will not have the power to bribe me and know in advance what are X and Y, or to choose what are X and Y. So then there's no arrow between lambda and X and Y, for example. And X and Y do not have any causal parents. Okay, so then the Bell DAG encodes all of those assumptions. It means that there are two ways of stating Bell's theorem. The first way is the way that I spoke about last lecture. That was like all of those assumptions give contradictional quantum predictions. And the second way is just look at this DAG and say, this DAG does not explain the quantum predictions. Here I say does not classically explain, because I'm basically saying that this DAG, when you look at this thing as a classical hidden variable, like as a classical node, then it does not explain the quantum predictions. I just noted that I spoke about those 3 assumptions, but I didn't speak about the background assumptions. And this is why the background assumptions are already encoded in the framework of causal inference itself. So in the framework of causal inference assumes that probability theory is true. It assumes that all of those nodes have classical values that are absolute, and everybody agrees that they are absolute. So indeed, this figure encodes all of these assumptions. Okay, any questions so far? Is this clear? What is the relationship between causal inference and Bell's theorem? Okay, in that case, I can ask you then, how can I causally explain these predictions? Because Bell's theorem just says that this DAG cannot causally explain the data that I see in the laboratory when I make a Bell experiment. So then how do I causally explain it? I still want to causally explain it, because I tried to convince you in the first part of the lecture that understanding causality is important, at least in the classical world. And I think in the quantum world, it's also important. So how can we explain it? There are many alternatives. The first alternative is to change the causal structure, of course, because I didn't say that the framework cannot explain. I only said that that specific DAG, like this specific Bell DAG, cannot explain. So these other DAGs, they can explain the probability distribution that we observe in a Bell experiment. However, they have problems. Can anyone tell me what is like an obvious, like the clearest first problem that you see when you look at this, like physical problem that you see that comes from this possible causal explanations?
I'm seeing that the space-like separation is not happening for like the first DAG.
Yeah, so good thinking. So here, Alice and Bob, they are space-like separated because you make them space-like separated in the experiment. However, this first DAG is kind of thinking that there is some way of causally connecting two things that are space-like separated. So that's true. And same kind of thinking. In this DAG, you have kind of Alice and Bob necessarily bribe me. I don't have free choice. I cannot choose X and Y independently. Lambda influences. And here, Alice and Bob, they choose the strategy lambda before I give them the number X and Y. So then here it's kind of something in the future is influencing something in the past. So the problems with these explanations are like this: superluminal causation, like causation that kind of goes faster than the speed of light. Like this is called superdeterminism, because like everything is predetermined. You don't have free choice to choose. Like I don't have free choice to choose what settings I'm going to give Alice and Bob. And this is retrocausality, because something in the future is causing something in the past. And of course, this is not like philosophically pleasing. This violates those assumptions that we want to keep. So in particular, this one violates relativistic causal error. This one violates independent settings, and this one also violates relativistic causal error. That basically says, because the relativistic causal error says that the cause of something has to be in the past like cone. Here it is in the future like cone, and here it is is space-like separated. Okay, however, as I mentioned last time, there are interpretations of quantum mechanics that violate those assumptions. And this is the way of seeing what those interpretations say in a causal framework. So when I told you that the interpretations of superdeterminism, they say that there is no free will. For example, that somebody mentioned that like Sabine Hossenfelder works on those interpretations. And there are some people that work. Then that's because this is the kind of causal structure that they think is explaining the experiment. There are people that work on retrocausality too, and then they think this is the kind of causal structure that explains the experiment. And there are the Bohmians, like Bohmian mechanics is an interpretation that has an arrow that goes outside of the light cone like this. Okay. However, it is important to remember that I told you that relativity theory tells us that you cannot send signals faster than the speed of light. But what this DAG says is that there is causation outside of the light cone. How is that possible? That is this thing in contrast with the things that we see in the laboratory? Like in the laboratory, we never saw signaling faster than the speed of light. Then how does this causal structure, like how does this interpretation, how does Bohmian mechanics deal with that? So this is why I spoke to you about fine-tuning before. And now I'm going to say another problem with those classical causal explanations. So there are two types of problems. The first problem is that it violates, the obvious one, that it violates those assumptions that it's important to us. But the second problem is that they have fine-tuning. So what does it mean? In the lab, we have always, in the history, observed this. So we never seen signals being sent faster than the speed of light. And this is why we believe in special relativity, because special relativity says that you cannot send signals faster than the speed of light. And we never saw signals being sent faster than the speed of light, so we believe this is true. However, those causal structures do not explain why this is true. Remember that the Bell DAG, meaning the simpler one, like this. Let me just go back. Yeah, so the Bell DAG, one of the constraints that a probabilistic distribution needs to obey in order to be compatible with the Bell DAG is the no signaling constraints, these ones. However, these other DAGs, they don't have the no signaling constraints. They have an arrow between X and B. So in principle, looking at this first one, in principle, B could depend on X if this was the causal explanation. However, those people that believe in this interpretation, they have to still explain, like, why is it that we never saw superluminal signaling in the lab? What happens is that their explanation is fine-tuned. Like I was saying before, you can have causation without signaling. If you choose the parameters of your model very specifically, so like in the other example that I have just the sum modulus 2. So here, basically, the way that B depends on its parents, on X, Y, and lambda, has to be very specifically chosen in a way such that there is causal influence, so you can violate the Bell inequalities, but there's no signaling. Like you have this causation without signaling. And this is fine-tuned. And in fact, this paper proved that every classical causal explanation, this paper from 2012, proves that every classical causal explanation that could explain Bell's, the violation of Bell inequality has to be fine-tuned. None of them can do both things at the same time. That is, explain why we don't see superluminal signaling and explain why we see violation of Bell inequalities. So that's a problem with every classical causal explanation. Okay, and this is a problem. Why is this a problem? That's also another question. Because when I showed you the cryptography example, fine-tuning was not a problem there, right? It was just how I devised the example, like very specifically chose. However, here it's not me, like it's not a person that devised, because before it was just me that devised that the encrypted message is going to be this function of the message and the key. But here it's not me, it's like nature. So it's like nature chose this very specific parameter to hide from us that there is causation between X and B. And this is a bit bizarre, And if someone is going to defend this type of interpretation, then they have to give an extra explanation, like other types of explanations on why why did we never see superluminal signaling? Why does nature has these very specific parameters? And it's kind of like your causal structure is not, that's supposed to explain what you see, is not explaining everything. But in principle, those are valid causal explanations. They just have those problems, like that they violate they violate assumptions that we like, and they are fine-tuned. Okay, do we have any questions about this, about the fine-tuning here? This is going to be important because Ela is also going to talk about it in the next lecture, about fine-tuning. No questions? Okay. Then now we have a problem, right? If all this framework that came from the 90s, that the statisticians developed, that explains causation and helps us figure out causation and everything, it doesn't help us figure out causation in the Bell experiment, because all of them have problems. Of course, you can subscribe to some of these interpretations, but if you don't want to accept those problems, then what can you do? That's where quantum causal models enter. So in the 2010s, we have developed this other framework that's called quantum causal modeling, which it's this type of solution for this problem from Bell experiment. And the idea of the solution is that we keep the causal structure the same. So the drawing is the same, but we change the way the causality works. This sounds very abstract, but concretely what this means is that you still have the same type of causal relationships, but now here you don't have a lambda anymore. You don't have a classical node. You're going to have a quantum node that's going to behave in the following way. Remember that before, the definition of a probability distribution being compatible with the causal structure was this one. So it's like children depend on parents, like A depends on X and lambda, which was the parent, B depends on Y lambda doesn't have anything, you sum over the latent variable. So now this is not going to be the definition of causation anymore, but the definition is going to be something like this, which I'm not going to explain everything because maybe many of you haven't seen mixed states or POVMs or trace, but basically those are quantum objects where this E represents measurements, this rho represents a quantum state that is here. And trace is like the summation, because you don't know what is the outcome of the measurements. And so here you can see that you have something that has the same flavor as before. It looks very different. The objects are very different, but you still have this idea of children only depending on parents. Because here, A, the measurement, like which measurement Alice is going to make, what is A, is going to depend on X and on rho, that is the state that comes from the quantum node. And B is going to depend on Y, and on rho, that is the state that comes from the quantum node. And then the summation is substituted by the trace. So it's an idea that we completely change the framework. The quantum causal modeling is a completely different framework for causality, but we still believe it captured some idea of causality because you still have this idea of children depending on parents. And now you have the same causal structure, but different way the causality works. And what are the constraints that you obtain now with this different framework? So we have that distribution PABC given XY is quantumly compatible with the Bell DAG if they obey this equation that I showed before. That implies in the following things. First, it implies no signaling. So this is still here. It's still a constraint. And it implies the zero-sum inequality. That is basically that the probability of winning is less or equal than the 85%, which is the quantum maximum. So now it explains the violation of Bell inequality, and it explains only up to the zero-sum limit, that is the 85%. So what this means that this new causal explanation can explain the quantum predictions without fine-tuning, because it explains to me why I don't see signaling faster than the speed of light, because this is one of the constraints now. Okay, so then the Bell causal structure is a causal structure where you can see a difference between the set of distributions that you can explain when the latent node is classical and when the latent node is quantum. But why is it cool to reformulate Bell's theorem in this causal way at all? Like, we already understood Bell's theorem before. This is just a way of kind of restating Bell's theorem and trying to find a way like to causally explain it. But why is that interesting? One of the things is that there are many other causal structures that also present quantum classical gaps. And this is something that we found out by doing causal inference research. So doing causal inference research, we found that these causal structures, for example, that's called the instrumental scenario. This is basically the, if you remember, the smoking, cancer, peer group, and gene. This is why it's called the instrumental scenario, because like that's the instrument that helps you figure out if you have an arrow here or not. And this one, that's the triangle scenario. Those are two examples, but there are many, many, many other examples of causal structures that we've looked at them from a class, like with where the nodes were classical variables, and we looked at them when the nodes were quantum systems, and we saw a difference in the set of probability distributions that can be explained. So that means that this point of view opens many possibilities of finding Bell-like theorems, because this is not going to give Bell's theorem because it's not the same causal structure, but it might give a theorem that is similar, of getting different applications. For example, I don't know, different scenarios where you can see that there is a quantum classical gap, like a difference between what you can do quantumly and what you can do classically. This can maybe even help us one day understand a little bit more about why do we have quantum advantage in computing? Like what causal structure, like if you organize your, I don't know, neural network as a causal structure, is this going to have an advantage by making it quantum or not? Then it depends on whether the causal structure has this quantum classical gap or not. And there are many others that we found that have. And there has even been experimental implementations of that. So like in the lab, people implemented something that was like the instrumental scenario, and they could obtain probability distributions that violate the inequalities, like they violate some constraints that come from this classical causal structure, but they are compatible with the quantum causal structure. Yeah, and that's it. That's what I was going to say. So thank you. Thank you so much for joining for these lectures. Are there any questions in anything that I said? Okay, if there are no questions, then just wanted to thank you again for joining for those lectures. These were all that I was going to say to you. And on Saturday, you're going to see Ila. I'm not going to be there because it's too early for me. And yeah, thanks for joining in those 2 days. And all the best. Just if you have a question that you were shy to ask, just send me an email. You can also send emails about like academia, life, or everything, not necessarily about the lectures. Okay. Thank you. Goodbye.